Good afternoon, my dear students. Today I am going to solve a new problem, moment of inertia. So the question goes like this: determine the moment of inertia of a given t section with respect to its centroidal axis. Now, to determine the moment of inertia with respect to its centroidal axis, first we need to determine the centroid. Now, to determine the centroid, I am assuming that there is a point capital C whose coordinates are capital X bar and Y bar. Capital C, X bar and Y bar. Now, capital C, X bar and Y bar are the coordinates of centroid for the entire given section. Now, the next step is we have to divide the given section into two rectangles. I'm just simply drawing a line over here such that it will become the first rectangle, the topmost one. It is the first rectangle and the next one is the second rectangle. And I'm assuming that for the first rectangle there is a point C1 whose coordinates are x1 comma y1, and let us consider there is a point C2 whose coordinates are x2 and y2. Now x1 y1 and x2 y2 are the coordinates of centroid for the first as well as the second rectangles, but x1 refers to the distance from the reference y-axis. Now just I am assuming that there is a reference y-axis towards the left side of the section, and there is a reference x-axis exactly at the bottom of the section. This is reference x-axis and here we have reference y-axis. Now x1 refers to this particular distance here from this y-axis to this point, and x2 refers to the same thing again, and C x bar refers to the same distance from y-axis. As you can see, all the 3 points are symmetric about this particular distance. x1 will be equal to x2 will be equal to x bar, as it is symmetric. The question here is we need to determine y bar. Now for the divided rectangles we have C1, x1 and y1. As we all know that x1 is the distance from reference y-axis, so it will be half of 80 millimeter, that will be 40, and y1 will be the distance from reference x-axis, that means from this particular line up to this point, so it will be 60. Up to here it is 60 plus half of 20, 60 plus 10 will be 70 millimeter. Similarly, we have C2 whose coordinates are x2 and y2. Now x2 and y2 can be written as x2 is the distance from reference y-axis, that is half of 80 again, so it will be 40 millimeter, and in the upward direction, I mean to say in the vertical direction, we have y2 which is half of 60, that will be 30 millimeters. Now we have a formula to calculate capital C x bar and y bar, which is equal to sigma ai xi divided by sigma ai and sigma ai yi divided by sigma ai. Now expanding the formula, x bar is equal to sigma ai xi divided by sigma ai, that is a1 x1 plus a2 x2 by a1 plus a2, and y bar which is equal to sigma ai yi divided by sigma ai, that is a1 y1 plus a2 y2 divided by a1 plus a2. Now for the first rectangle we have the dimensions 80 millimeter by 20 millimeter, hence a1 will be equal to 80 multiplied by 20, that is 1600 millimeter square, and for the second rectangle the dimensions are 60 and 20, hence a2 will be equal to 60 multiplied by 20, that is 1200 millimeter square. 1200 millimeter square. Okay, now substituting all the values in here, a1 is 1600 multiplied by x1 is 40 plus a2 is 1200 multiplied by x2 is 40 divided by 1600 plus 1200. So obviously the value of this one will be equal to 40 millimeters. Now calculating y bar, we have x bar which is equal to 40 millimeter, we have to remember this one. Y bar 1600 multiplied by y1 is 70 plus 1200 multiplied by y2 is 30 divided by 1600 plus 1200. Now we have y bar which is equal to 52.85 millimeters. Capital C x bar comma y bar which are equal to 40 millimeter comma 52.85 millimeters. This point over here, that is 40 millimeter and 52.85 millimeters. Now if I draw a horizontal line which is passing through the centroid, right? Now this line can be taken as centroidal x-axis. Similarly, when I draw a vertical line which is passing through the centroid again, now this distance or this particular line can be taken as centroidal y-axis. Now the next step, we need to calculate the moment of inertia of this entire section with respect to centroidal x-axis and centroidal y-axis. Now I have redrawn the sketch once again. So we have capital C over here. I'm drawing a horizontal axis which is representing the centroidal x-axis, which is lying exactly at a distance of 52.85. Now from particular distance here, right, it is located exactly at a distance of 52.85 millimeters. Similarly, for the first rectangle, there is a center, right? So I'm calling this one as capital X and X. Now similarly, I'm drawing a horizontal line which is passing through C1. So we have C1 over here. Now C1 is located at a height of 70 millimeter. I'm calling this one as X1 and X1. Similarly, I'm drawing a horizontal line, right, which is representing X2 and X2. This line is located at a height of 30 millimeters. Now all these are from reference x-axis. From here it is 30, from here it is 52.85, and from the same bottom axis it is located exactly at a distance of 70 millimeters. Now we need to calculate the moment of inertia with respect to centroidal x-axis. The formula is Ixx is equal to sigma Ixx, I small x, plus area multiplied by hy square. Now there are two rectangles over here. I'll take Ixx1 for the first rectangle, moment of inertia with respect to centroidal x-axis for the first rectangle, plus area 1 multiplied by hy1 square, plus same thing again Ixx2 plus a2 hy2 square. Now here hy1 is the difference of y bar and y1, and hy2 is the difference of y bar and y2. We have y bar which is 52.85, y1 is 70. The difference of both will be 70 minus 52.85, and over here it is 52.85 minus 30. Now the values will be 17.15 millimeter and 22.85 millimeters. Okay, we know that moment of inertia of any rectangle with respect to its centroidal x-axis will be BD cube divided by 12. Now, whatever the formula you are seeing here, I am expanding that formula. So for the first rectangle, right, we have this one that can be written as B1 D1 cube divided by 12 plus area is B1 multiplied by D1 multiplied by hy bar. Hy1 can be taken as y bar minus y1, or difference of y bar and y1 square, plus b2 d2 cube divided by 12 plus b2 multiplied by d2 is the area multiplied by y bar minus y2 square. Now substituting all the values, we have b1 which is equal to 80 millimeter multiplied by d1 is 20 cube divided by 12 plus 80 multiplied by 20 is the area, 1600 multiplied by, we have calculated hy1, that is 17.15 square, plus b2 is 20 multiplied by 60 cube divided by 12 plus 1200 multiplied by 22.85 square. Now calculating, we get Ixx, which is equal to, we get moment of inertia with respect to centroidal x-axis, that is equal to 1510476.33 millimeter to the power 4. Now to calculate, okay, we got one of the answers here, moment of inertia with respect to centroidal x-axis. Now to calculate moment of inertia with respect to centroidal y-axis, Iyy will be equal to sigma, same thing again, Iyy plus area multiplied by hx square. Now expanding the formula, we get Iyy1 plus a1 multiplied by hx1 square plus Iyy2 plus a2 multiplied by hx2 square. Now you need to remember one thing here, hx1 as well as hx2 both will be equal to 0. I'll tell you how. Now when I'm drawing a vertical line which is passing through the centroid over here, right, now this bigger line, right, is taken as y bar. It's taken as y bar. And similarly, when you draw a vertical line which is passing through the C1, right, this can be taken as y1 and y1. Similarly, y2 and y2. Now all these lines are lying on the same straight line, hence there is no difference between these lines. So hence hx1 and hx2 will be equal to 0. Now the only thing we need to do is just to calculate iyy1 as well as iyy2. These two values will be equal to 0. Now iyy1 will be equal to d1 b1 cube divided by 12, and plus iyy2 will be equal to d2 b2 cube divided by 12. Now the values will be 20 multiplied by 80 cube divided by 12 plus 60 multiplied by 20 cube divided by 12. Now finally calculating the value of iyy, we'll get the value as 893333.33 millimeter to the power 4. Now these are the values. Thank you.